Hello. Okay, what I want to do now is talk about the first derivative test from section 4.4. And I've in the past when I've taught this, sometimes starting off with all the terminology and the words and all this kind of stuff, it gets kind of clumsy. And I think what I want to do for this situation is just work through an example. So what I'm thinking of doing is just working through number 13 from section 4.4. And that is we're given the function f of x equals x to the third minus 6x squared plus 2. And we're asked to find any local extrema. So the idea is to determine whether it's a local max or a local min. That's what we're hoping for. So in order to do that, we need to find the critical numbers. And what we're basically going to do is talk about the regions to the left and to the right of each of those critical numbers. So let's first of all find the critical numbers. In other words, I got to take the derivative of f of x. So the derivative is equal to 3x squared minus 12x. And that can be factored into, I can see a 3x is common, 3 is common, and x is common. Therefore, that leaves me with x minus 4. So I end up with the derivative is equal to 3x times x minus 4. Set that equal to 0. And that tells us that either 3x equals 0, which means x must equal 0, or x minus 4 equals 0, which means x equals 4. So I've determined that there are two critical numbers, 0 and 4. Now, the biggest thing I want to do now is get an orientation, draw a number line, and put them in order on the critical numbers in order on the number line. So I've got 0 here and 4 here. And now I want to see how the slope is changing when it comes to the critical number, okay? So what I'm going to do is look at the region to the left of 0, between 0 and 4, and to the right of 4. So it's a matter of picking a number in that region, a value of x, plugging it into the derivative function, and just recognize what the slope is in each of those regions. So to the left of 0, over here, notice that I'll pick the easiest number to work with. -1 is just right there. That'll be the number I pick. Number x equals -1. Between 0 and 4, 1, 2, or 3, 1, you can pick any number you want, but 1 is right there. 1's easy to work with. And number bigger than 4, the smallest integer numbers are easiest to work with, but 5 is the smallest integer, and it seems like that'll be the easiest to do a calculation with. So what we've got now, I need to plug in the values. Let's look at what f of x is. It's the f prime of x is equal to 3x times x minus 4. And the original function itself is equal to x to the third minus 6x squared plus 2. So I've got 3 values I want to plug in. Notice I'm concerned about the slope in the region. So I'm going to plug each of the values into the derivative function. That's f prime of -1 equals, what do we have here? -3 times -1 minus 4, which is -3 times -5 is 15. That's positive 15. So I've got a positive. The thing I'm concerned about is the sign. So when you're doing these problems, the goal is just to determine what the sign is. But if you're showing your work, I'm going to ask you to determine, let me see how you know it's positive. And if you can show the negative times the negative somehow, that would, in working the problem out, that would indicate that it's positive. But anyway, positive 15, solving the actual number and getting the answer also works. But let's plug in now f of 1. What do we get? When I plug in 1, I get 3 times 1 minus 4, which is 3 times minus 3, which is minus 9. So I got a minus 9, and the biggest thing there is that I got a minus sign. So over here, the first leftmost one, it's positive, so the slope, the line is looking like this. This in the middle is negative, so it's looking like this. Right? The slope is negative. And then the last one, f of 4, no, we want to plug in 5, excuse me. We plug in 5, f of 5 is equal to 15 times 5 minus 4, which is 15 times 1, which is 15, which is positive again. We got a positive 15. So this line looks here like this. So now that we've determined the slope and the situation there, how it looks, what we got to do is just determine, compare what's happening when you get to the 0. So in other words, that first 0 at x equals 0, here, we're up here. Notice, if you come in from the left, it's positive slope, and to the right it's going down, negative slope. So that means we must be at the top. And that means we've got a local max at x equals 0. That's kind of cluttered there. But anyway, and notice the other one. When you're down here in this situation, you come in from the left, the slope is negative, therefore it's going down. And then as you go off to the right, it goes up. So you're at the bottom. And it turns out you've got a local min at x equals 4. So now let's figure out what those values are. Well, we've determined whether it's a local min and a local max, but let's look at the wording right for how we're going to answer the question. So we're worried about what the value is at x equals 0. So f of 0 gives us 0 minus 0 plus 2, which is 2. So f of 0, we have the point 0, 2. And then we've got at f of 4, we've got 4 cubed minus 6, 4 squared plus 2, which is 444, that's 1664, minus 6 times 16 plus 2 equals 64 minus 96 plus 2. That's minus 32 plus 2 is minus 30. So we've got the coordinates 4, negative 30. So the wording of it is, from what we've got up here, we've got a local max. The max value is 2 at x equals 0. And local min is negative 30 at x equals 4. Okay, so that is what we use the first derivative test to determine whether we had a local max or min. Now, at the beginning of the function, when you're looking at the problem, you can see it's a cubic function, so cube looks like this. And our function's got some additives in there, so we know it's going to look like this. So, and because it's a positive x cubed, it goes down when you go to the x to the left, and positive, it goes up when you go x to the right. So you could tell that got a max here and a min, so it turns out 0 and 4, so you can see the max is going to be at 0, and the min is going to be at x equals 4. And then the values you get from plugging those two values into the function. And that's what the answer is at the bottom. Okay, so that's the general format of it. How you can tell if it's a max or min. And now I would like to read to you from the wording of the situation to see what the first derivative test, the way it's worded, is this: that when you've got, let's see here, let me make sure I'm going in the right place. Yeah, okay, so now the first derivative test, the function f is continuous on an interval. And notice that c is a critical number, so it's like c is 0. One of ours in this problem was a 0. And 0 to the right, and you had a value to the right and the left, and 0. So what our situation was, if f prime, if the slope is greater than 0 to the left of the critical number, that's our 0, and the slope is less than 0 to the right of 0, as it did in our diagram. From 0 it went down. then f of c is a local max. So we had our critical number, f of 0 was the local max. Notice that's the y value is the local max. Ours was at c, which is x equals 0, but it is f of c is the local value itself. And then notice the second one, the local min occurs if the slope is negative. That happened, this is, and to the left, this is for our 4. So to the left of 4, as it was coming in, it was going down. We have the negative value. And then as you go off to the right from 5 on up, the slope is positive as you go off to the right. So that means it was at f of c is at the bottom, which means it's a local min. And that was at negative 30. So the situation that, look at the very bottom thing here, if you notice down here on the screen at the very bottom sentence there, that if the slope, if the derivative, f of x, has the same sign on both sides, then you don't know. Then f of c is neither a local max nor a local min. It's not that you don't know. It's not a max or a min. You've got the same sign, so there's something else going on there. Okay, we'll see an example like that and talk about that a little bit later on. But that is the idea, and that's using the first derivative test to determine what the local extrema are. All right, so I wish you well, and I'll talk to you a little bit downstream.